Welcome to the drag force, part 2, where we use first-year calculus and u substitution the way the AP grader wants you to find an equation for the velocity of a projectile in the air on its way down, experiencing a drag force directly proportional to its velocity. Please note that just because the AP grader expects you to do u substitution and separation of variables, it doesn't mean that you have to. Notice you can find any equation off a graph by making sure you have correctly graphed the early behavior, preferably at 0 if you can get it. Any initial values you have, initial slopes or anything else, the late behavior of a graph, final slopes, final values if you have them, and connecting them clearly and continuously without any sharp corners or sudden turns, which are non-differentiable and don't exist in the real world, making sure you've got their correct concavity taking you from one slope to another. If you've got your exact intercepts or your exact asymptotes, you can label them, and that will enable you to fit an equation to the graph. This works for the drag force, and it works in any differential equation where you have the derivative equal to the original function with a minus sign out front to make it decay instead of growth, and some collection of constants out front. However, if you particularly enjoy u substitution, here is the official first-year calculus way of how to solve an equation that looks like this. Let's start from the very beginning. We said you were going down, and that would have been that, and that would have been your acceleration going down if it hadn't been for this pesky drag force. Let's set up our differential equation, move this to the left side so we can see what we're doing, divide everything by m so we can get our derivative by itself. We will have a equals g, aha, we expected that, minus b over m, pull those constants out front, calculus style, times v. And that means that the derivative, dv dt, is g minus quantity b over m times v. U substitution and separation of variables says each letter should only appear on one side. And if we're over here, then the fact that there's a b on the left and a b on the right is going to prevent us from doing anything remotely helpful. First step is we've got to move the t to the other side. You've never seen an integral with two d's on one side. This is going to be no exception. Move the dt to this side. And move everything else to the other side. Why everything else? Oh, look at those horrible parentheses. This is a product. You cannot add or subtract to both sides without having the problem of that dt. We have one dt. Again, we'll put that on the left because it looks cleanest. And the rest we're going to have is this inexcusably ugly critter, g minus quantity b over mv in the denominator with dv on the top. Ew. I mean, come on, we were shooting for dv over v, and if we had it, it would be great, but we don't. Well, we're just going to have to do something to get d something over something. In calculus, you call this u substitution, and the rule for u substitution is that u is everything ugly that you hate and you wish weren't there. See this? Fits that description like anything. Everything ugly you hate and you wish weren't there. There is u. Now, if that's u, what is du? Well, I don't know what du is, but I can figure out du dv, take the derivative of this puppster. This goes away. That's a constant. Very nice. Negative b over mv. Take the derivative of that with respect to v. You've got negative b over m. That means du is negative b over m dv. All right, we have dv. Well, we can make it negative b over m dv if we really want. We'll muck up the equation a bit, but we can do that. And that'll give us negative b over m dt equals, there we have it, du over u. Now, we are ready to integrate. Anti-differentiate this, anti-differentiate that. Let's see, we only have one variable on this side, and that's t. dt, we are dealing with t. Bless my soul, there isn't any. So, before the function was this, we took the first time derivative of this, and it gave us that. No, we're not done yet, but we might as well do all the hard stuff on the hard side. What function has a derivative of its own reciprocal? This is not a power here. This is not a polynomial. If this were u to the negative 2, we could follow our power rule. Say it used to be u to the negative 1, only it got multiplied by negative 1, so we have to divide by negative 1. But watch this. This is u here to the negative 1 power. And if you add 1 to negative 1, what do you get? Uh-oh, you get 0. U to the 0 is 1. The derivative of 1 is 0. This is the 1 power of u, for which our lovely polynomial rules, a to the n minus 1, and turning it on its head, does not work. This is one that you need to declare a math major and do all sorts of interesting partial derivatives and path integrals before you can prove the answer, or you can get it from some senior who took calculus last year and tells you that the function whose derivative is the reciprocal of the function is the natural log. I got it from some AP Physics student who was in BC Calc while I was in AB, and I pass it on to you. You'll be able to prove it in approximately 3 years. Hang tight. It'll be your sophomore year after you've declared your math major, and it will be so satisfying. In the meantime, integral du over u is natural log of u. Remember it, it gets you out of pickles. Please note that both of these are indefinite integrals. They are no one's friend, and they come with that pesky plus c on both sides. Hey, we could have 2 constants that we don't know, or we could move this one to the other side and have 1 constant that we still don't know. Well, we didn't know it before, so no harm done there. Now, this is a natural logarithm. That's nasty. Let's move that constant to the other side. Hey, we still don't know it, so no harm done. Now, we can at least put natural logarithm of base e to this and say something sensible like u equals e to the negative b over mt plus some sort of constant here. And what was u? Oh yes, u was g minus b over mv. Now we're getting somewhere. We wanted some sort of function that was e of t. Now, before we go any further, we've got a constant way up here. And we have some nice rules about exponents. And one of them says e to the negative bm over t plus c is really equal to the product of this and that. And this was always some random number we didn't know. So instead of calling this e to the c, can we call it some nice number for a leading coefficient like this? Maybe solve around? Now, let's get v over here on the right and move this hairy thing over here on the left. We've almost got it. We've almost got v by itself. Now we just need to multiply both sides by m over b. If you think you can take it from here, pause the video and take it from here. If you're still frozen, or if you get stuck, press play to see the rest of the algebra. Ready? Here we go. Bless my soul, we have our old friend mg over b minus b over m times some number we don't know, e to the negative b over m t, very nice, equals v. Now, same as before, we've got boundary conditions. We have when t equals 0, b equals 0. And that means whatever this number is that we still didn't know, mg over b jolly well has to equal this number times e to the negative b over m times 0, which is just 1, which means this number has to equal mg over b. Looks good so far. We have velocity as a function of time equals, pull out a common factor of mg over b, 1 minus e to the negative b over m t, also known as our terminal velocity, and the beautiful flipped exponential decay that we saw when we fitted the equation to the graph directly. Ladies and gentlemen, separation of variables in U substitution for the drag force done in less than 12 minutes. Our conclusion is the same as it was before. An object will pick up speed at a rate of 9.81 meters per second squared, but not for long. It will soon pick up less and less speed as it did before, until finally the drag force BV equals the weight going down, at which point it will fall at a constant speed for our purposes of mg over b as per model number 1.